Okay, in this session we're going to talk about viscous boundary layers, which are an important phenomenon when dealing with inviscid flows, surprisingly enough. Usually, when you deal with these inviscid flows, we just use the Euler equation, which is what's covered in part 1b fluids here. This is the first order equation. It's non-linear, but there's no nu del squared u term. So there's nothing coming from viscous dissipation. And remember what we said in one of the earlier sessions on basics of fluid mechanics, that if a flow is initially irrotational, it will remain so unless there is some vorticity generated by viscosity at boundaries. So the key problem with modelling these flows with the Euler equation is if we were to model, say, this flow here, this horizontal flow, just with the Euler equation, because it's first order, we can only impose one boundary condition. And so our flow would look like this. And down next to a solid plate, we lose our no-slip boundary condition, and the velocity drops to zero instantly, or suddenly, which is clearly quite unphysical. So the idea of adding a boundary layer is there's this small region where viscosity is actually really important, just at the interface between the exterior flow and where it hits a boundary. Now, you can achieve some success ignoring boundary layers. There's some problems with water flow past obstacles and everything that makes perfect sense, but one of the most notorious examples is something called a von Karman vortex street, where you have a horizontal flow coming into an obstacle like this, and it turns out that this object will shed vortices like this in a really nice regular pattern, because vorticity is generated by viscosity at the boundary. So this might be a very, very inviscid seeming flow, but just right on the boundary where viscosity is important, that will generate vorticity and produce these quite shocking patterns. A good example of this, if you look at the clouds in the atmosphere going over an island, you'll often see little cloud patterns shed in the wake of the island. So a good approximation for the thickness of this boundary layer, delta, is just the length scale over which vorticity diffuses from the boundary. So if we go back to our vorticity equation and just consider the diffusive balance, so d omega by dt, it's got a scale a little bit like nu, which is our kinematic viscosity, grad squared omega. So if we take scalings of these terms, we have omega over t scales like nu omega over L squared, or not L squared, but delta squared, thickness of this boundary layer, and that gives us that the boundary layer grows like the square root of the viscosity multiplied by time. So the thickness of the boundary layer increases in time, but the thickness of the boundary layer also increases as the viscosity increases, which is what we'd expect. So we're going to derive some more general boundary layer equations that we can use when dealing with these. So let's just start by considering an external flow that is just a big horizontal uniform, well, not necessarily uniform, but we just have u is equal to capital U, which is possibly a function of x in the x direction. And our boundary layer is probably going to look something like this, with some delta, its thickness, and a horizontal length scale L. So outside the boundary layer, we've just got Euler's equation here. We're balancing a time derivative in capital U with an advective term here and a pressure gradient. But inside, we're just going to apply full Navier-Stokes, and we're going to see what happens. So let's first do some scalings. So the horizontal length scale is L. It's L. And also, the dominant flow outside is purely horizontal, so we can get a time scale, because U scales like this horizontal length scale divided by time, which implies that time scales like the length scale divided by U. And so we can go back to our delta is equal to the square root of nu t, and find that this is actually equal to square root nu L over U. And now let the vertical length scale Y scale like this delta. Okay, the first balance that we're going to carry out actually comes from this equation here, and this shows that P over L scales like rho U squared over L, and that gives us that the pressure scales like rho U squared. That will be helpful later, we'll come back to that. The next scaling we're going to make is this balance here that comes from incompressibility inside the boundary layer, so U over L scales like V over delta. That implies that v scales like delta u over L, and we also have that delta over L scales like root nu over ul, which is actually just the reciprocal of the square root of the Reynolds number. So v actually scales like Reynolds number to the minus 1/2 times u. So in flows with a very high Reynolds number, very inviscid flows, the vertical velocity is comparably small with respect to the horizontal velocity. So now let's go and scale the x and y components of Navier-Stokes, as we did for lubrication theory, for example, and see what comes out in terms of the boundary layer equations. So here's all the scalings we had last time, and the equation outside the boundary layer, which is just repeated up here for clarity. So, like we've seen many times before, this term scales like u squared over L, because t scales like L over u, so divide by t, and you end up with u squared over L. This term here is u squared over L, and just to prove this to you even more, this is delta u over L, that's the v, times u over delta, which is indeed u squared over L. So the left-hand side scales like u squared over L. dp by dx, well, p scales like rho u, or left-hand side scales like rho u squared over L, rather. P scales like rho u squared, so dp by dx scales like rho u squared over L. The same argument we used to neglect the horizontal derivatives in lubrication theory works here, that actually u over L squared is much, much less than u over delta squared, because delta is much, much less than L. So therefore, this term here, we can ignore this derivative, and we just say that this term scales like mu u over delta squared. Now, what is mu u over delta squared? Well, mu u over delta squared is mu u over nu L over u, which is actually just rho u squared over L. So every single term in the horizontal momentum equation, except for this horizontal part of the Laplacian, scales like rho u squared over L. So we don't really get to throw much away here. In this equation, on the left-hand side, this scales like uv over L, again using the fact that t scales like L over u. This quite clearly scales like uv over L, and this here scales, surprise, surprise, like uv over L. To get there is a little more involved. We have to rescale one of the v's in terms of u and L, but you get there eventually. Now this term here will scale like rho u squared over delta, because that's just dividing pressure by the y scale. Again, we can kill this term because it's beaten by this one here, and this term here multiplied by the mu just scales like mu v over delta squared. So let's compare the left-hand side, which is equal to rho u v over L, with this term here, which is just our pressure, and this term here, which is our Laplacian. Okay, so first of all, we're going to take the ratio of pressure term, rho u squared over delta, to the Laplacian term, mu v over delta squared. And when you work this out, this just comes out to be the Reynolds number, which is much, much bigger than 1. So the pressure term wins out over the Laplacian. Now we'll compare the pressure term, rho u squared over rho u v over L, so comparing it to the left-hand side here. And this comes out, again, to be the Reynolds number, which is much, much bigger than 1. And so the dominant term in the y equation is just dp by dy, which equals 0. So pressure is just a function of x in the boundary layer. It does not depend on the vertical direction. Okay, so if we're going to be collect all of this together, we end up with the horizontal equation here. All we've lost is d2u by dx squared, which we scaled away. And what have we done here? Well, last time this term here was minus dp by dx. If you go back a slide, that's what we had here. However, we know that dp by dy is 0, and we want pressures to match. So this is only in the boundary layer, but we need this to match with the outside flow. And in the outside flow, we go back to the equation for the outside of the boundary layer, this one up here at the top, we see that minus dp by dx is just rho du by dt plus u du by dx. So we've just substituted that in here. So the outside flow gives dp by dx is equal to minus rho d capital U by dt plus u du by dx. So that's how we got this term in here. And let's think a little bit about the boundary conditions. So we need no penetration on the boundary. That implies that V is 0. And we need no slip. We can impose a no slip condition because we're dealing with viscosity here. So this is U equals 0 and Y equals 0. And this just comes from matching with the outside flow. So great, we've derived some general boundary layer equations. Now can we apply these to a certain problem? And the classical problem, which is first solved here by Blasius, is just the boundary layer over a flat plate. Now we've got an outside velocity u, which is just a constant in this case, blowing over a plate where the only length scale here is actually just so this is x, this is y. The only length scale is x itself. And so that implies that our boundary layer thickness is just nu x over u, or alternatively mu x over rho u. So great, we've got a boundary layer thickness. Now what happens to our governing equation? Well, we still have rho du by dt plus u du by dx plus v du by dy, but this term here is 0 because we just have an outside flow u that's constant, and this term here is 0 because du dx is 0. So we're just left with equals mu d2u by dy squared. We also have that div u is 0. So that means that we can write u is equal to d psi by dy and v is equal to minus d psi by dx for a stream function psi. Now the best way to solve an equation like this is with a similarity solution. And I won't go into full detail about how similarity solutions work. You'll encounter them in many different places. But here's the general thinking behind the form of psi that is posited here. So we know that d psi by dy has to scale like u. And we also know that we expect y to scale like delta. So introduce a similarity variable eta, which is equal to y over delta. That means that psi over delta scales like u, but is not necessarily equal to it. It might be modified by some factor. So we can just write psi is equal to u delta of x, function of this eta variable. This is the justification behind finding similarity solutions. So we look for solutions of this form here. Now, we can find out that the partial derivative of delta with respect to x is just going to be 1/2 delta over x. The partial derivative of eta with respect to y is going to be 1 on delta. And the partial derivative of eta with respect to x is just going to be minus y on delta squared times delta over 2x, which is just going to be minus eta over 2x. Great. Okay, with these tools, that allows us to write u is equal to uf prime of eta, and v is equal to, this one's a little bit more involved. We have contributions from differentiating this with respect to x and differentiating this with respect to x. So we have a contribution that looks a little bit like u over, or form that looks a little bit like u over 2x times eta f prime of eta minus delta f of eta. Okay, with those tools we can plug them in to the equation up here. So this is what we, sorry, I missed a term here. This should be a delta here as well. Yes, I'm happy with there being a delta there. Because this term here, the u delta, yeah, I'm happy with that. Great. Okay. So these are our governing equations. We can substitute these in to this equation here, and we end up with just an equation for f. Let's have a little think about what the boundary conditions need to be. Well, we know that u equals 0 on y equals 0, and this transforms to eta equals 0, so f prime equals 0 on eta equals 0. We also know that v equals 0 on y equals 0, so that implies that f equals, so this term is going to be 0 when eta is 0, so we also need f equals 0 when eta equals 0. And finally, we want u to tend towards capital U as eta goes off to infinity, as y over delta becomes large and we go into the main flow. So we just need f prime goes to 1 as eta goes to infinity. So to sum this up, that's the equation we end up with once you substitute. For f, and these are the boundary conditions we derived earlier. Now this can be solved numerically by a technique called shooting. And what this is we apply some boundary conditions. So this is a third order DE. We know that f equals f prime equals 0 at eta equals 0. So we try f equals f prime equals 0 at eta equals 0, and f double prime is equal to some constant. And then we solve the ODE and work forward and see what it tends to as we go to infinity. And then we come back and change what our constant is and keep correcting until we get a solution that works. So this is actually quite a well-known numerical technique that's used in a lot of different problems. Many commercial boundary value problem solvers use a shooting method. MATLAB has some built-in methods that don't, but shooting is the most common way to solve this problem. But this gives us a similarity solution that was first derived by Blasius for the boundary layer on a flat plate. And with that, that is kind of all you need to know about boundary layers going into part 3. If you want to cover that in a little bit more detail, though, as always, here's some suggested reading.